Kia ora and welcome back to another intriguing video on atomic structure part 2. Today we're going to look at compounds. Understanding compounds will allow us to start to unravel and work out what is going on through chemical reactions. So join me now, sit tight and make plenty of notes. Here we go. Let's first start with equations. Equations are simple ways of us showing quite a complex system of reactions taking place. For example, we understand photosynthesis, but actually understanding what's going on the subatomic level is really important. Here you can see the equation for photosynthesis. Now we're not going to get into the whys and the hows of this equation just yet. We're going to focus on a few other things. These numbers here, these letters here, and this little number there. Let's break it down even simpler. Let's look at H2O. H2O is the symbol for water. We know from our last video that hydrogen and oxygen are found in the molecule of water. If we were to draw it through using atoms, it would look something like this. And you've often heard me describing it as the Mickey Mouse molecule. Throughout this next section, we're going to have to focus on the symbols more than the words. The symbols, again, scientists being quite lazy, are the key to equations. Linking it back to ions, now that you understand what they are and how to use them, I'm going to teach you a little cheat way of working them out. Let's use water again. We know that water is two hydrogen atoms and an oxygen. How do we know how many hydrogens and how many oxygens we need to combine together to make water? All of us know it is H2O, but why do we need two H's and one oxygen? Well, it starts with understanding the ionic charge of a hydrogen ion. We should remember that hydrogen should have a positive ionic symbol because it wants to get rid of one electron, making it positive. Oxygen, on the other hand, should have a 2-. This is because it needs 2 electrons to complete its outer shell, therefore making it more negative. To simply work out how many hydrogens and oxygens we need in a molecule of water, we can do the swap and drop method. All we do is move the ionic symbols and numbers down to each of the opposite atoms that we're trying to work out. For example, here you can see the 2- is going to travel down to the hydrogen, and the 1+ is going to travel down to the oxygen. We'll end up with something that looks like this. And you can kind of start to see H2O taking shape. Here we have hydrogen with the 2-. We have the oxygen with the 1+. Now, in chemistry, we never write the ones. Okay, so that's why we just had the plus before. When we've done the swap and drop method, we get rid of any ones and the symbols, so the minus and the positive. And we should be left with H2O. As you can see here, guys, the minus is now gone, the positive is now gone. But what do other things mean? Well, compounds, like water, are when 2 or more different elements come together and are chemically bonded. We often see 2 numbers when looking at these sort of equations, and we just looked at water before, and can see in photosynthesis we have another number with the 2. Whenever we see a large number in front of a compound, we know that this means how many of this particular compound, both the hydrogens and the oxygens, are found in this equation. So a 6 here would indicate 6 water molecules. The smaller number indicates how many of the particular element that is present directly to the left. So here we have 2. That means there are 2 hydrogens in this water molecule. If we see nothing, like we see next to our oxygen here, that means there is only 1 of this atom within this molecule. Let's look at CO2. You can see the 6 means that there are 6 carbon dioxide molecules. Each of these 6 carbon dioxide molecules has 1 carbon, because there is no number next to it, and 2 oxygens, designated by the small number 2 here. Remember, this little number only tells us that there are 2 of the oxygens, the immediate atom to its left, not the carbon. We will look at brackets when we come across equations later in the topic. So, 6 H2Os means that in this reaction we have 6 molecules looking like this, bouncing around and reacting or being pulled apart in photosynthesis. If you were asked to tell me how many hydrogens were in this equation, at this part of the equation, we would look at the numbers and we can combine them together. So if I was to count how many hydrogen atoms we can see within the water molecules, you could just count these single ones up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A much quicker way of doing this, however, is to take the 2, because we know there are 2 hydrogens per water molecule, and we know that there are 6 water molecules, and times those 2 by how many we have. So 2 times 1, 2, 3, 4, 5, 6. You can see I've written that here. For hydrogen, 6 times 2, and it equals 12. Exactly like counting it, but a bit faster. And we can do the same for oxygen. So we know there's actually a 1 here. There's only 1 oxygen. 1 times 6 is 6. And we can see that here. 1 big one here, 2, 3, 4, 5, 6. So you can see, this is actually making it a lot easier to see what is going on. Because if we had to draw this for every reaction, you can imagine what trying to draw photosynthesis is going to be like. Now, some other information that might confuse you a little bit. We have to name certain things, depending on whether they're cations or anions. So, cations are pretty simple. They are the metals, and all we add at the end of a metal to make it an ion is a metal ion, this word here. So sodium becomes a sodium ion. Non-metals are a little bit different. We have to add an "ide" on the end. Okay? So if we take chlorine, for example, chlorine becomes chloride. We swap the "ine" at the end of chlorine with "ide". Now there are a few different endings to each of the non-metals. For example, oxygen. So you just have to rote learn these, as there's no hard and fast which part of the end word you take out. Fluorine, for example, is similar to chlorine. We take the "ine" off the end of that and just add "ide". Other things to know, we have these things called sulfates. You might notice this from sulfuric acid, H2SO4. A sulfate, okay, is a sulfur bound with some oxygens. A nitrate is nitrogen bound with some oxygens. The way I remember this is if you see a sulfur by itself, it's on its own. So you would use the "ides," I am by myself. If you see sulfur, for example, bound with something else, like a couple of oxygens, it's found some mates, so you add the "ate" to the end. So, to summarize, you can read the following points in your own time. As always, gentlemen, here are your quiz questions that I'll be quizzing you on in our next lesson. For those of you that really want to push yourself, have a crack at the extension question. Hope you've learned something, gents. Catch you in class.